PWM, pulse width modulation, is the common and easy way to generate an effective analog signal without an actual digital to analog converter. It won't work always, like it won't work for generating sound in a speaker, but it works for most things. Pulsing refers to turning voltage on and off. Your PWM output pin from a microcontroller, such as an Arduino, will turn between the positive terminal, so probably your 5 volts, and the negative terminal, your 0 volts, your reference, your negative, your ground. Basically turning it on and off and on and off. That's your pulsing. Width is how long the pulse is. If we count this as a square wave, on and off, then the width would be the wavelength. And modulation means changing how much of the wavelength is devoted to on or off. Is it on half the time? Is it on a quarter of the time? Whatever. So it's a square wave generator, but it's a square wave of voltage. And if you hook this up to a multimeter, it will read a voltage between 0 and your max voltage, because it sort of averages over time. Your multimeter might take a reading every half second to a second. And it gives the effect of a different voltage because of how quickly it switches. Perhaps every 500ths of a second, 500 hertz. So if you're using it to switch an LED on and off, you switch it faster than the human eye can see. If you're trying to power something, basically turning something on and off very, very rapidly often will give nearly the same result as if you had given it that actual different voltage. Again, not always, but often enough that it's a very common mechanism. It's one way to control computer fans, too. You can control their speed with PWM without them actually having some sort of full-on control system. Now, there's not really much left with PWM except to show you. So now I'll show you. So I will be using my homemade oscilloscope here. Here's a simple program. We'll begin at 500,000 baud to write the data to the oscilloscope program on my computer. This is where you read the value and write it as fast as it can, which is much less than 500,000 times a second. This is just making sure the data get there very quickly. This is the part that's not part of the oscilloscope. I'm going to analog write, which is PWM, pin 3, and 64. So it takes a number between 0 and 255. 0 refers to not anything at all, essentially 0 volts. 255 refers to the max, so that would be, essentially 5 volts always on. Actually, it would be 5 volts always on. Anything between 0 and 255 will turn that 5 volts on and off, or you could view it as switching between 5 volts and 0, that much of the time. 128 would be 50%, 64 is 1/4. So 25% of the time, it's going to be on. 75% of the time, it's going to be off. So I will now hook up my Arduino, and I will upload this program. And now the Arduino has set up its PWM and is beginning to transmit. I will now open my oscilloscope. We have the port name, 500,000 baud, standard settings, we connect. And now, because nothing is plugged into that analog port, it's a floating input. This is it measuring me just moving the Arduino around. So I will now connect pin 3, digital pin 3, this is the one generating the PWM signal, and I will plug it into analog port 0. The analog ports are read-only. So I've now plugged it in, and if you have the full resolution, you can very dimly see way up here some dots moving, way down here some dots moving, because it's alternating between maximum and minimum. Let's make it easier to see. Let's make it even easier. So now I'm taking the samples as only 8 pixels high and stretching them, because we already know it's either the top or the bottom pixel. So now you can see these at the top, this is where it's high, this is where it's 5 volts. These are smaller, and the ones at the bottom are bigger. This is where it's 0 volts. That means the bottom, it's 0 volts for more time. Now, let's try to make this not move as much. So, because it's moving very slowly, that means we're close to the right value. So let's try increasing it just a little bit. And it slowed down. Let's try 542. It slowed down, but it also started going the other way. So if I were to go one more, it would speed up. See? So 542 is about the best we're going to get right now. Now what I could do is I could double that, increase it, and get twice as many on the screen. But that'll make it harder to see. This is pretty much close enough. I need to implement a pause function. A real oscilloscope would, of course, already have one. So what do we see here? This is basically, you're taking a photograph of the phases. A photo. Now, it allows you to see much easier the fact that it goes low for a certain amount of time, then it switches to high. And see, the gap here is the same as the not gap here. This gap is the same as the not gap here. Switching back and forth. That's all the PWM signal is. Switching back and forth. It's like having a light switch, turning it on 25% of the time. Now, we can actually estimate the duty cycle from this. And I'll use the same math that I would with a real oscilloscope. It's only a difference of accuracy. The number I give you is going to be wildly off. It'll be in the ballpark, but it's not going to hit the first baseman. So the first thing we do is try to count how many of these we have, which is, of course, easier said than done, but there is one trick I can use. The snipping tool to take a screenshot, and then it'll just freeze it. Let's let it move so it's a nice even multiple. And now we'll count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So it's about 32 across the screen. So if we look at our display width, we have 542 samples. We're using a group size of 1, so no grouping. So 542 samples, roughly how long 32 is. So if we go over here to our calculator, we take 542 samples divided by 32. So this is basically samples per window, and this is cycles per window. So that gives us samples per cycle. So if we divide samples per cycle by samples per second, we're going to get seconds per cycle. And it's rough to estimate, this is going to be wildly wrong, but let's say it's about 8,300. So we're getting about that many seconds per cycle. So what if we take this and divide 1 with this? We're getting 490 hertz. That is cycles per second. We just flipped it. We took the reciprocal. And that is about right. From what I have heard, the Arduino has about a 500 hertz duty cycle. So about 500 times a second, one of these, high to low, 25% high, 75% low, will complete. So there you go. A real oscilloscope would be able to give you a much more accurate number, but we got a lot closer than I thought we would. So that's PWM. Because it's happening about 500 times a second in this case, it is well more than the human eye can detect, which means we can dim an LED. We can cause a transistor to transist as if we had a lower voltage through it. We can supply a lower voltage to a multimeter. We can supply an effective lower voltage to a fan, except we're not actually giving it lower voltage, we're turning it on and off. A fan might not even turn on if you give it too low of a voltage, but if you just turn it on and off fast enough, it'll keep its inertia. Every time you turn it off, it starts to slow down, but then you turn it back on, it speeds back up, and you can control its speed. So that's why I say effective voltage. You can control things that don't work with lower voltages, as if they did. You need a certain voltage to turn a diode on, but if you use the max voltage, you're always turning it on. But if you, for example, if a diode requires 0.7 volts to turn on, you can make it act as if you were only giving it 0.4 volts, and it'll be on, even though it shouldn't turn on, just because you're turning it on and off so rapidly. It's as if it worked. That's the power of PWM. Also, it's a whole lot easier to create circuits with it, because it's cheaper to simply turn something on and off than to create an entire digital to analog converter. And that's about all there is to say about PWM. A simple concept. Just turn it on and off, and it works great. You're still going to need a full digital to analog converter for making music, but you can use this for most things, and it's especially easy to make the circuits. We will make our own, of course, in the future, but for right now it's much easier to just use the Arduino. So until next time, be seeing you.